Hello everyone. This is Roshan, and today I will going to take week 7 live session on solid mechanics course. So we have completed now 6 weeks, and today I will discuss the lectures which is based on week 7. So week 7 cover 3 lectures which is based on the strain matrix in cylindrical coordinate system and the linear momentum balance in cylindrical coordinate system. So week 7 comprises three lectures, lectures 17, 18 and 19. So let's begin the today's session. Week 7. So in this we have 3 lectures. The first 2 lectures is based on linear momentum balance in cylindrical coordinate system. Linear momentum balance in cylindrical coordinate system. And the last lecture is based on strain matrix in cylindrical coordinate system. A strain matrix in cylindrical coordinate system. So first I will briefly explain the overall concept that is being used in these lectures, and then after I will solve some problems which is based on this lecture, so that you can understand the concept more in a more better way. So yeah, let's start the today's session. So first of all, in the lecture, the first lecture of the linear momentum balance. So basically in this lecture, in the similar way, LMB, that is linear momentum balance equation, has been derived as we done in the previous weeks, which is based on the Cartesian system. So the similar approach were used to derive the linear momentum balance in cylindrical coordinate system. So I just simply write the final expression that we get after deriving the LMB in cylindrical coordinate system. So yes, LMB. So the first equation is LMB in cylindrical coordinate system. So linear momentum balance is based on basically Newton's second law, which state the sum of total force due to traction plus sum of total force due to body force is equal to rate of change of linear momentum of the body, that is d by dt of p. So this is actually the total LMB equation. Okay, so the final expression that we got for the traction force, total traction force, is given by this equation, where Ft is total force due to traction, Fb is total body force, and the third expression, that is d by dt, is the rate of change of linear momentum. Rate of change of linear momentum. Okay, where Ft is given by del sigma zz upon del z Ez plus del tau theta z upon del z E theta plus del tau rz upon del z into Er plus del sigma rr upon del r plus sigma rr upon r times Er plus del tau theta r upon del r plus tau theta r upon r into E theta plus tau z r upon r. Sorry, plus, so here I write del tau theta r upon del r plus tau theta r upon r into E theta plus del tau z r upon del r plus tau z r upon r times Ez, and the last term is 1 by r del tau r theta upon del theta minus sigma theta theta into Er plus 1 by r tau r theta plus del sigma theta theta upon del theta times E theta plus del tau z theta upon del theta into Ez times delta V. Okay, so this is basically the total traction force, and if we see the terms, so this is on this is the total traction force, the total force due to traction on jet plane. This is the total traction force on the y plane, sorry, r plane, because in cylindrical coordinate system we have three planes: r plane, theta plane and z plane, and this is basically the stress resultant, that is the total force due to traction on the theta plane, and this whole term is multiplied by delta V plus some higher order of delta V. Similarly, the body force is given by, that is the FB, total body force is given by BR that is body force along along r direction times ER plus B theta E theta plus BZ EZ times delta V plus higher order of delta V. Similarly, the rate of change of linear momentum d by dt of P is given by rho, which is the density of the body, times AR ER, where AR is the acceleration, radial acceleration of the body, plus A theta E theta plus AZ EZ times delta V plus higher order of delta V. And if we balance these three equations, which is equation number 3, 2 and 1 with this equation, okay, then we get the final LMB for the for this problem, that is the LMB equation in cylindrical coordinate system. So I just simply write the equation, that is LMB equation in r direction, theta direction and z direction. So LMB equation in r direction. The LMB equation in r direction is given by del sigma rr upon del r plus 1 by r del tau r theta upon del theta plus del tau rz upon del z plus sigma rr minus sigma theta theta upon r plus br is equal to rho times ar. So this is the LMB equation in r direction. Similarly, LMB equation in theta direction. LMB equation in theta direction. So it is given by del tau theta r upon del r plus 1 by r del sigma theta theta upon del theta plus del tau theta z upon del z plus 2 times tau r theta upon r plus b theta is equal to rho times a theta. And the last one is LMB equation in z direction. So it is given by del tau zr upon del r plus 1 by r del tau z theta upon del theta plus del sigma zz upon del z plus tau zr upon r plus bz equal to rho times az. So this is the three equations which we use to solve our problem. Okay, so this is the three LMB equations. So as you see these equations, when we compare these equations with the equations of LMB in Cartesian coordinate system, we see that the equations for cylindrical coordinate system are quite different when we compare with the Cartesian coordinate system. So yeah, whenever we work out with the cylindrical coordinate system, please be cautious while using the equation, because it is different, because there is some term, there are some term which is extra to the term in addition to the Cartesian coordinate system, because in Cartesian coordinate system we don't have this term, this type of term, that is sigma r minus sigma theta theta upon r. So this is the overall LMB equation in cylindrical coordinate system. And the last lecture, so the first two lectures are based on these only. The whole derivation, if you see the lectures, this three equation has been derived in the first two lectures, and the last two lecture is based on the strain matrix in cylindrical coordinate system. So I just simply write here, that is strain matrix in cylindrical coordinate system. A strain matrix in cylindrical coordinate system. Okay, so as we know from the previous lectures that strain matrix, which is the strain tensor basically, is given by half of grade u plus grade u transpose. I already mentioned it in the previous lectures, so you can go through the previous lecture and see the expression of this strain tensor. And when we write it in the Cartesian coordinate system, then it is given by, I just simply write here so that you can compare with the strains in cylindrical coordinate system. So I am writing it in, first I am writing it in Cartesian coordinate system, that is in E1, E2, E3 coordinate system. So it is given by del u1 upon del x1, sorry, del u1 upon del x1 half of del u1 upon del x2 plus del u2 upon del x1 half of del u1 upon del x3 del u3 upon del x1. Similarly here, because strain matrix is symmetric, so we can simply write here half of del u1 upon del x2 plus del u2 upon del x1 del u2 upon del x2 half of del u2 upon del x3 plus del u3 upon del x2 half of del u1 over del x3 plus del u3 over del x1 half of del u2 over del x3 plus del u3 over del x2, then del u3 over, sorry, del u3 over del x3. Okay, so this is the expression for the strain tensor in E1, E2, E3, but here we want the strain tensor in cylindrical coordinate system. So the final expression, that is the strain tensor in cylindrical coordinate system, it is given by, that is in r, theta and z coordinate system. So it is given by del ur over del r half of, sorry, half of 1 by r del u r over del theta minus u theta plus del u theta upon del r, half of del u r over del z plus del u z over del r, half of 1 by r del u r over del theta minus u theta plus del u theta upon del r, 1 by r del u theta upon del theta plus u r, 1 by 2 del u theta upon del z plus 1 by r del u z upon del theta, and the last column is given by half of del u r over del z plus del u z over del r, and here half of del u theta upon del z plus 1 by r del u z upon del theta, and the last one is del u z upon del z. So this is the expression for the strain tensor in cylindrical coordinate system, that is in r, theta and z direction. Now we will see the physical significance of each strain component. So the first component is epsilon rr, that we call as radial strain, okay, longitudinal strain, or we simply say radial strain. So yeah, physical significance of epsilon rr. So it is called, basically epsilon rr is called longitudinal strain. Okay, and it is given by, basically it is given by epsilon er dot with er is equal to del u r upon del r. So this is actually the longitudinal strain or radial strain. The next one is physical significance of epsilon theta theta. So significance of epsilon theta theta. So this strain is called hoop strain or circumferential strain. So it is called as hoop strain or circumferential strain. Hoop strain or circumferential strain. It is given by epsilon theta theta, which is equal to epsilon e theta dot with e theta, which is also equal to, if you see the component of epsilon rr, it is so it is mentioned here 1 by r del u theta upon del theta plus ur, that is 1 by r del u theta upon del theta plus ur. So this is the expression for circumferential or hoop strain. So here ur is the displacement, that is the radial displacement, and u theta is the basically tangential displacement, and here it is given as the first derivative of u theta with respect to theta plus ur times 1 over r. So using this formula we can find out the circumferential or hoop strain. The next strain is basically, so this strain is nothing but actually elongation of a line element, directed along theta direction. directed along theta direction. The next strain that is mentioned here is the shear strain, basically, that is gamma r theta. Gamma r theta. So it is given by gamma r theta, which is nothing but 2 times of epsilon r theta. So it is given by 2 times epsilon er dot with e theta, which is nothing but equal to half of del u r over del theta minus u theta plus del u theta over del r. So this is the expression for the gamma r theta. Okay, I think everyone is understanding the concept here. Now this is the relation of strain in terms of displacement. Basically this represent a strain displacement relation. The next thing that we have to discuss here is the relating strain and stress in cylindrical coordinate system, that is a stress strain relation, which is nothing but a constitutive relation also. So stress strain relation in cylindrical coordinate system for isotropic material. So I am writing here stress strain relation in cylindrical coordinate system for isotropic materials. Okay, so for isotropic material we are writing here the case where the strain is represented in terms of stress, that is epsilon. The first one is epsilon theta theta, that is nothing but the circumferential strain. Epsilon theta theta is given by 1 over e sigma theta theta minus nu times sigma rr plus sigma zz. Similarly, epsilon zz equal to 1 by e sigma zz minus nu times sigma rr plus sigma theta theta. And next one is gamma r theta, which is given by tau r theta upon z gamma rz. So this is analogous to the expression which we derived in the Cartesian coordinate system. Next is gamma theta z, which is given by tau theta z upon z. So this is the stress strain relationship in cylindrical coordinate system. So this is all about these 3 lectures. I have mentioned all the important formula that is given in the lecture. So this is all about the lectures part. Now we will move on to the problem solving session. So based on these concept, I will solve some problems through which you will better understand the concept using questions. So let's start the problem solving session first. So the first problem is problem number 1. So this is the problem based on the equilibrium equation in cylindrical coordinate system. So the question is verify that the following stress field satisfies the Z equation of equilibrium, Z equation of equilibrium in the absence of body force. In the absence of body force. Okay. So the question is sigma r is given as A times Z by r cube minus 3r square Z upon r to the power 5. Sigma theta theta is A Z by r cube. Sigma zz is minus A times Z by r cube plus 3 Z cube by r to the power 5. Now next one is tau rz, which is given as minus A times r by r cube plus 3z square r upon r to the power 5, and the other term, that is tau r theta tau z theta, is 0. Here also mention that big R square equal to small r square plus z square. So we have to basically check the stress field, whether the stress field in the satisfy the Z equation of equilibrium or not. So the Z equation of equilibrium in cylindrical coordinate is given by, so I am just solving this question. The Z equation of equilibrium in cylindrical coordinate is del tau zr upon del r plus 1 by r del tau z theta upon del theta plus tau zr upon r plus del sigma zz upon del z plus rho b naught, or we say rho bz, equal to 0. So there is no body force, so it ultimately is 0. And here from this expression we can write del r upon del big R equal to b small r upon r, and del r upon del z equal to z by r. Okay. So we have to find all these one, that is del tau zr upon del r, del tau z theta upon del theta, tau zr upon r, del sigma zz upon del z. So we will find these terms individually. That is, the first term is del tau zr upon del r, which is given by minus A times del by del r by r cube plus del by del r 3r z square upon r to the power 5. And if we calculate this, we will find the final expression is minus A 1 by r cube minus 3r upon r to the power 4 del r upon del r plus 3z square by r to the power 5 minus 15 r z square upon r to the power 6 del r upon del small r. So this is the final expression that we get. Upon further manipulating, we find that the final expression will become minus A 1 by r cube minus 3r square upon r to the power 5 plus 3z square upon r to the power 5 minus 15r square z square upon r to the power 7. Okay. The next one is del tau z theta upon del tau z theta upon del theta. So this is 0. It's already given in the question, I guess. Yes, del tau z theta is 0. So the derivative is also 0. Next is t tau rz upon r, which is nothing but minus a up into 1 by r cube plus 3z square upon r to the power 5. The next thing is del sigma zz upon del z. So del sigma zz upon del z equal to minus a 1 by r cube minus 3z upon r to the power 4 del r upon del z plus 9z square upon r to the power 5 minus 15z cube upon r to the power 6 del r upon del z. So the final expression that we will get is minus a times 1 by r cube minus 3z square upon r to the power 5 plus 9z square upon r to the power 5 minus 15z to the power 4 upon r to the power 7. And now when we evaluate this, that is del tau zr, del tau zr, del tau zr upon del r plus tau rz upon r plus del tau zz upon del z. Because the other two terms are 0, z theta term, if you see the z theta term is cancelled out, the only three term will left, del tau zr upon del r plus tau zr upon r plus del sigma zz upon del z. Okay, so the final expression will become this one, minus a times 3 by r cube minus 3r square upon r to the power 5 minus 3z square upon r to the power 5 plus 3z square upon r to the power 5 plus 9z square upon r to the power 5 minus 15r square z square upon r to the power 7 minus 15z to the power 4 upon r to the power 7. So plus 3, yeah. No, minus a times 3 by r cube minus 3r square upon r to the power 5 minus 3z square upon r to the power 5 plus 3z square upon r to the power 5 plus 3z square upon r to the power 5 plus 9z square upon r to the power 5 minus 15r square z square upon r to the power 7 minus 15z to the power 4 upon r to the power 7. Now if we take common, that is r square plus z square from all the terms, we will get minus a times 3 by r cube minus 3r square plus z square upon r to the power 5 plus 15 z square upon r to the power 5 minus 15 z square r square plus z square upon r to the power 7. Now if you see this expression, so 15z square upon r to the power 5, and here it is, that is nothing but minus a times 3 by r cube minus, what is r square plus z square, that is r square, so 3r square upon r to the power 5 plus 15z square upon r to the power 5 minus 15z square r square upon r to the power 7. Now if you see this, so this become r cube and this will cancel out. Similarly, z square upon r to the power 5, so this will become 5 and this will cancel out again. 15z square upon r to the power 5, minus 15z upon r to the power 5. So ultimately the final answer is 0. So we have proved that it satisfies the equations of equilibrium in z direction. So this is problem number 1. Now next problem is based on the similar approach, that is based on the equilibrium equation. Problem 2 is, given the following stress field in cylindrical coordinate, given the following stress field in cylindrical coordinates, which is sigma rr is equal to minus 3 p z r square upon 2 pi r to the power 5. Sigma zz is given by minus 3p z cube upon 2 pi r to the power 5. Sigma tau rz is minus 3p z square r upon 2 pi r to the power 5, and the other terms are 0, that is sigma theta theta equal to 0, tau r theta equal to 0, and tau z theta equal to 0. And here also r square is equal to z square plus r square. So the question is, verify that the state of stress satisfy the equilibrium equation in the absence of body forces. Question is, verify that the state of stress satisfies the equations of equilibrium in the absence of body force. Equations of equilibrium in the absence of body force. Okay, so the solution is, so here the question is not asked about that we have to satisfy the equation of equilibrium along any specific direction. Here the question state that we have to satisfy the equation of equilibrium in all the three directions, that is r, theta and z direction. So one by one we prove that equilibrium equation along r direction, along z direction, along theta direction is 0. That means it satisfies the equation of equilibrium. So the first one is equation of equilibrium along r direction, that is del sigma rr upon del r plus del tau r theta upon r d theta plus sigma rr minus sigma theta theta upon r plus del sigma rz upon del z. So this will become del by del r of minus 3pz r square upon 2 pi r to the power 5 plus 1 by r minus 3p z r square upon 2 pi r to the power 5 plus del by del z minus 3p z square r upon 2 pi r to the power 5. So this will get minus 3pz upon 2 pi r to the power 5 del by del r square plus minus 3p z r square upon 2 pi del by del r 1 by r to the power 5 plus 1 by r minus 3p z r square upon 2 pi r to the power 5. So here only I will put the values that is given in the question. So after substituting the values of each the stresses, we evaluate the overall expression. Plus minus of 3pr upon 2 pi r to the power 5 del by del z upon of z square plus minus 3pz square r upon 2 pi del by del z of 1 by r to the power 5. So it will ultimately gives So after manipulating and solving this each term, we will get minus 15 pzr upon 2 pi r to the power 5 plus 15 pzr cube upon 2 pi r to the power 7 plus 15 pz cube r upon 2 pi r to the power 7, which is equal to, and if we take common, that is 15 pzr upon 2 pi r to the power 5, we will get 15 pzr upon 2 pi r to the power 5. We are taking common from each term, plus 15 pzr upon 2 pi r to the power 7. So the left term is r square plus z square. And what is r square plus z square? This is nothing but basically big R square. And if you compare these two terms, this is actually minus. If you compare these two terms, so it will ultimately cancel out and the final expression will be 0. So the equation of equilibrium in r direction is satisfied. The next equation that we have to satisfy is equation of equilibrium in theta direction. So del tau theta r upon del r, del tau theta r upon del r plus 2 times tau r theta upon r plus 1 by r del sigma theta theta upon del theta plus del tau theta z upon del z. So if you see the question, that is, there is no stress in theta direction, that is sigma theta theta, tau r theta and tau z theta all are 0. So this will become 0, this is also 0, this term is also 0, this term is also 0. So it is automatically satisfied. So this equation is automatically satisfied. And the last equation of equilibrium is along the equilibrium equation in z direction. So we have to satisfy those equation, that equation also. That is, we have to satisfy del tau zr upon del r plus 1 by r del tau z theta upon del theta plus tau zr upon r plus del sigma zz upon del z plus rho naught b, rho naught basically rho bz equal to 0, because there is no body force, this is actually 0. So this will become del by del r of tau zr, and tau zr is minus 3p z square r upon 2 pi r to the power 5 plus 1 by r del by del theta of tau z theta, and tau z theta is, what is tau z theta? So if you see in the question, tau z theta is 0 basically. Yeah, so this term will cancel out. The next term is tau z r upon r. So this is 0 actually. The next term is tau z r upon r. So 1 by r, what is tau z r? Minus 3p z square r upon 2 pi r to the power 5 plus del by del z of sigma zz. And what is sigma zz? Given the question, it is minus 3p z cube upon 2 pi r to the power 5. Okay, and if we take the derivative with respect to r and z, we will get minus 3p z square upon 2 pi r to the power 5 plus minus 3p z square r upon 2 pi and del by del r of 1 by r to the power 5 minus 3p z square upon 2 pi r to the power 5 minus 9p z square upon 2 pi r to the power 5 minus 3p z cube upon 2 pi del by del z of 1 by r to the power 5. The next thing is minus 3p z square upon 2 pi r to the power 5 plus 15 p z square r upon 2 pi r to the power 6 into del r upon del r minus 3p z square upon 2 pi r to the power 5 minus 9p z square upon 2 pi r to the power 5 plus 15 pz cube upon 2 pi r to the power 6, and this will become del r upon del z. Okay, now we are summing the expression which is common. So which has common term, we are actually summing that expression. Minus 3pz square upon 2 pi r to the power 5, and what is del r by del r? Del r by del r is actually r by r. So 1 by 15p z square r square upon 2 pi r to the power 7 minus 3p z square upon 2 pi r to the power 5 minus 9p z square upon 2 pi r to the power 5 plus 15 pz to the power 4 upon 2 pi r to the power 7. So this is the final expression that we will get. Now taking this common, this term this is the term, so it will become actually this 15p z to the power z is to the power 4 upon r to the power 7. And here it is minus 3p z square upon 2 pi r to the power 5. So if we take r to the power 5 common, that is minus 15. If we take this and this common, okay, if we take this and this common, so what we get? We get minus 3p by 2 pi r to the power 5 minus 3p by 2 pi r to the power 5 z square plus r square, and here it is minus 9p z square upon 2 pi r to the power 5. 9p z square upon 2 pi r to the power 5. And now this term 15p z square r square upon 2 pi r to the power 7 and 15p z square. So here we are taking common 15p z square. Actually we are taking common upon 2 pi r to the power 7. So it will, the common term is r square plus z square. And if you compare this one, z square, here also z square, and yeah, so r to the power 7 here, okay, so this become minus 3p z square plus r square is nothing but, so I am r square I am replacing it with z square minus r square. Okay, so yeah, this term will give us minus 3p z square upon 2 pi plus 15p z square upon r square 2 to the power 7 and minus 3p z square upon 2 pi r to the power 5 minus 9p z square upon 2 pi r to the power 5. Okay, so this will become 9 and 3, that is, so if we sum this term, this three term, 9p z square, 3p z square and 3p z square, that is minus 15p z square upon 2 pi r to the power 5. So this is the only term that is left here, and this is here. Yeah, and what is minus 15p z square upon 2 pi r to the power 5 plus, and r square plus z square is basically r square, bigger square. So 15p z square bigger square upon 2 pi r to the power 7, So this 2 and this 7 is cancelled out by 7, and this 2 term will become then equal, which cancel out actually, and this is finally become 0. So we have satisfied that the above set of stress components satisfy the equation of equilibrium in cylindrical coordinate system. So this is all about problem number 2. The next problem, that is problem number 3. Problem 3. So here the question is, given the following stress field, given the following stress field in a thick wall elastic cylinder, given the following stress field in a thick wall elastic cylinder, that is sigma rr is given as a plus b by r square, sigma theta is given as a minus b by r square, sigma r theta is given as tau r theta, tau r z, tau theta z, tau z z, sigma z z, all are 0. And so the question is, so in this we have 3 part of the question. So here where a and b are constants, a and b are constants. Okay, so the first question is, verify that the given state of stress satisfies the equations of equilibrium. The equations of equilibrium in the absence of body forces. In the absence of body forces. The second part of the question is, find the stress vector on cylindrical surface. Find the stress vector on a cylindrical surface. Find the stress vector on a cylindrical surface r equal to a. And the third part of the question is, if the surface traction on the inner surface, if the surface traction on the inner surface that is r equal to ri is a uniform pressure pi, is a uniform pressure pi, and the outer surface r equal to r naught is free of surface traction, find the constants a and b. Find the constants a and b. So this is the question. I am repeating once again the question. So the question is, given the following stress field in a thick wall elastic cylinder, sigma rr is given here, a plus b by r square, sigma theta is given here, that is a minus b by r square, tau r theta, tau r z, tau theta z, sigma zz equal to 0, where a and b are constants. And the question is, verify that the given stress satisfy the equation of equilibrium in the absence of body forces. And the second part is, find the stress vector on a cylindrical surface r equal to a. And the third part of the question is, if the surface traction on the inner surface r equal to ri is a uniform pressure pi and the outer surface r equal to r naught is free of surface traction, find the constants a and b. So the first question is on satisfying equilibrium. So yeah, let's begin from here. Solution part of this question. So here tau r theta, tau r z, tau theta z, sigma zz all are 0, and sigma theta theta depending only on r. If you see the sigma r expression, sigma theta theta expression, so it is only depending on r, depending on r. So we need to check only r equation of equilibrium. Because the theta, because there is no z component of stress, so it automatically satisfies the equations of equilibrium in z direction, and along theta direction there is a stress component, but it is independent of the theta coordinate. So that's why that is also automatically satisfied. The only remaining equation is the left, that is equation along r direction. So we have to satisfy only this equation. Yeah. So the r equation of equilibrium is given by del sigma rr upon del r plus 1 by r del tau r theta upon del theta plus sigma rr minus sigma theta theta upon r plus del tau rz upon del z. So del sigma rr upon del r is minus 2b upon r cube, 1 by r del tau r theta upon del r is, there is no del tau r theta, so it automatically is 0. This cancel out. Sigma r minus sigma theta theta upon r, sigma r minus sigma theta theta is basically 2b upon r square. To 2b upon r cube, and this is also no 0. So if you see, this is also 0. So yeah, equation of equilibrium is satisfied. Thus we can say that all equations of equilibrium are satisfied. All equations of equilibrium are satisfied. Okay, so this is the first part of the question. The second part says, find the stress vector on a cylindrical surface at r equal to a. So we have to find the stress vector, that is basically the traction vector, and we have known the component of a stress tensor. So using the traction and stress relation, that is T equal to sigma, and we can find out the traction vector on surface at r equal to a. So first we have to find the direction of the unit normal to the surface at r equal to a. So B part of the question is, the unit outward normal vector to a cylindrical surface at r equal to a is n equal to er, because A is along radial direction and it is given that surface at r equal to a, so it is along, the unit vector is along radial direction. Does the stress vector on the, so the traction vector on this surface, the traction vector on this surface is tr t theta tz, is given by sigma rr sigma theta theta 0, and all the other terms are also 0, and it is along er direction. The unit normal vector is along er direction, so the component along er direction in er e theta ez coordinate system is given by 1 0 0. The final term that is left is sigma rr 0 0. So the traction vector is sigma rr er plus 0 e theta plus 0 ez, which is finally become a plus b by a square, because it is calculated at r equal to a into er. So this is the traction vector or surface stress vector on the surface at r equal to a. So this is the second part of the question. Now the third part of the question is, if the surface traction on the inner surface, so if the surface traction on the inner surface r equal to ri is a uniform pressure pi and the outer surface r equal to r naught is a free of surface traction, find the constants a and b. So yeah, so basically we have given boundary conditions, that is question number C. So here we have given boundary conditions. So the boundary conditions are at r equal to r naught, that is outer radius, it is mentioned that traction, sorry, what is given in the question? Traction free, surface is traction free, so basically there is no radial stress, that is sigma rr equal to 0. And at r equal to ri there is some pressure acting, which means sigma rr equal to minus of p, because this is a compressive stress, which means a plus b by ri square equal to minus pi, and a plus b by r naught square equal to 0. Okay, so find the constants a and b. The question is to find the constants a and b. If we subtract both the equation, we will get b upon ri square minus b upon r naught, subtracting the second equation from the first equation, so we will get b by r naught square minus b by ri square equal to 0 minus of minus pi, that is pi. So b will become 1 by r naught square minus 1 by ri square equal to pi. So b will become pi ri square minus r naught square, sorry. So it will become, if we take the LCM, we will get my ri square minus r naught square upon ri square r naught square equal to pi, which will give b equal to pi into ri square r naught square upon ri square minus r naught square. So this is the value of b, and the value of a is minus pi minus b by RI square minus pi minus b by RI square, that is minus pi r naught square upon RI square minus r naught square. And if we take the LCM, minus pi Ri square minus r naught square minus r naught square upon Ri square minus r naught square. So r naught square, sorry, this will not cancel out. Minus p common, Ri square minus, so this is plus r naught square. So this and this cancel out. The remaining term that is left is minus pi Ri square upon Ra square minus r naught square. This is the value of A, and this is the value of B. Okay, so this is about question number 3. Now coming to the next question, that is question number 4. Problem 4. So this question is also based on the equilibrium equation and the stress-strain relationship. So the question is, think of an isotropic solid cylinder which is glued to a rigid plate at both its ends. The two rigid plates the two rigid plates are then pulled apart. The two rigid plates are then pulled apart along the axis of the cylinder. Along the axis of the cylinder. Such that the normal of the rigid plates remain aligned with the axis of the cylinder. With the axis of the cylinder. It turns out that u theta is 0 in this case, but ur and uz do arise. Okay. Furthermore, cylinder is such. Furthermore, ur and uz are not functions of theta coordinate. Assume that the deformation of the cylinder is such that every planar cross section of the cylinder that is jet plane or axial planes remains planar after deformation. Remains planar after deformation. After deformation, but it does change its radius. But it does change its radius. So the questions are, we have 3 questions based on the statement above. That is, the first part of the question is, what can you say about the dependence of UR and UZ on radial and axial direction, on radial and axial coordinates. That is R comma Z. The second part of the question is, obtain the strain matrix and the stress matrix for the above problem. And the stress matrix for the above problem. The third part of the question is, show that the theta component of stress equilibrium equation is automatically satisfied. And the last part of the question is, what boundary condition will be used in order to solve the above deformation problem. So these are the 4 parts of the above question. That is problem number 4. I am repeating the question one more time. Please see carefully. So the question is, think of a isotropic solid cylinder which is glued to a rigid plate at both its ends. The 2 rigid plates are then pulled apart along the axis of the cylinder, okay, such that the normals of the rigid plate remain aligned with the axis of the cylinder. It turns out that the u theta is 0 in this case, but ur and uz do arise. That means u theta is always 0 in this case, but ur and uz may not be 0 always. Furthermore, ur uz are not function of theta coordinate. It's also mentioned in the question that UR and UZ are not function of theta coordinates. Assume that the deformation of the cylinder is such that every planar cross section of the cylinder, that is jet plane or axial plane, remain planar after deformation. That means there is no out of plane deformation happen in this case. The only deformation that will happen is the change of radius, that is along the radial direction there may be a change in the line element, but there is no change, that is there is no out of plane deformation happen in this case after the, but it does change its radius. So yeah, in the question it's mentioned already that the problem in this problem the deformation is such that the radius may change. So the first part of the question is, what can you say about the dependence of the UR and UZ on radial and axial coordinate R and Z? The second part of the question is, obtain the strain matrix and the stress matrix for the above problem. Third part the question is, so that theta component of a stress equilibrium equation is automatically satisfied. And the fourth part of the question is, what boundary conditions will be used in order to solve the above deformation problem? So let's begin with the solution of this problem. This is a very good question by the way. So I'm now, so first of all I will draw the figure for this question because it's a very good question and important question through which you can understand the radial, that is the cylindrical coordinate system, in a better way. So yeah, solution part. So we have one cylinder and it is clamped in a fixed plate. Okay, this is the origin, this is along z axis, and this, suppose the length of the cylinder is L, so this is L by 2 and this is also L by 2. And it is mentioned in the question that the two rigid plates are then pulled apart along the axis of the cylinder. So basically the cylinder is pulled apart along the axis of the cylinder. So there is a stretching happen in the cylinder from both the direction. And it is also mentioned that this cross section remain fixed. That means the size of this cross section will not change after deformation. So after deformation, the cylinder will not look like this. That means this section will be fixed, but due to stretching, there is some decrease in the radius in the center of this cross section, center of this cylinder. So the final figure that we'll see after deformation is this. In this way, we can say. So after deformation, because it's now stretched, so original figure is of this length. Suppose this is L by 2 initial, this the overall length of the cylinder is L, and after deformation it has gained some length from both the direction, from both the ends. So it is nothing but the displacement delta, or we say it is prescribed displacement. Okay. So the first part of the question is, what can you say about the dependence of UR and UZ on the radial and axial coordinates R and Z? So as you see, the rigid plates are glued to ends of the cylinder, and end cross section can neither shrink nor expand because it is fixed, so it can neither shrink nor expand. But as the plate is stretched, because it is stretched, pull apart, and therefore the cylinder undergoes extension, which means that cylinder radius of the cylinder will be non-uniform in between the two plates. So we can say that there is a displacement along z direction, and as the displacement happen in the z direction, there is also decrease in some radius. So first of all, there is a decrease in radius in between, and there is some increase in radius, as you see in this figure, some decrease in the figure radius in between due to the displacement along z direction. So yes, the first we can say that UR, that is a displacement, that is a radial displacement, is a function of z. Also, a radial displacement, that is UR, is also a function of R, because as R equal to 0, at R equal to 0, you can see that R equal to 0 here, where R radius is equal to 0, sorry, uh, so you can see that this is the radius where the R equal to 0. So at this line, at the center line, there is radius at R equal to 0, there is deformation is also equal to 0, that means UR equal to 0. But as you increase the radius, you can see that there is a displacement. So we can say that UR, that is the radial displacement, is also a function of R. So from this figure we can conclude that UR and UZ, so UZ is also a function of R and UR is also a function of R. And along with that, UR is also a function of Z. So solution is due to extension of cylinder, the the radius due to extension of cylinder and fixed due to extension of cylinder and the ends of cylinder are glued with rigid plate, therefore the radius of the cylinder, therefore the radius of cylinder will change non-uniformly. And due to this, we can say UR is a function of Z. Along with that, UR will also depend on radius, because it's 0 at R equal to 0, but it's non-zero for other values of R. For other values of R. Okay. Now think about the UZ, that means the displacement along z direction. So as we stretch the cylinder along z direction, you can see that there is a displacement along z direction, but is it depend on the radial coordinate? That means, is it depend on the radius? Because if we stretch something, it doesn't mean that, because if you see, you can see here that z direction is here and this is the radial direction. Okay, so you can see that if it is dependent on the radius, then at every z, that means at a particular z, the radial displacement, that is a displacement along the at z direction, will also depend on the radius. That means here, suppose it is extended by, suppose 1 mm, so here it also it is extended, it will extended by some amount 0.8 mm, here it is 0.6 mm, so it means that it is dependent on the radius also. But here if we stretch the cylinder, there is a equal displacement coordinate along z direction. That means it is independent of the radius. And it is also mentioned in the question that the cross section remains planar after deformation. That means there is no out of plane deformation happen. That means after the deformation, the circular cross section remains circular. There is no out of plane deformation. This means that there is no radial dependence. That means at a particular cross section, each point in the cross section radially, that means shifted by the same amount. So, then only now the cross section will remain planar. Suppose I have this plate, there is a plate and this is planar plate, and this is a cross section. Okay, suppose this is a circular cross section and here the radius is 0, and if this point move along z direction by this amount, and this point will move by this amount, this point will move out little less amount, and this will not move. So you can see that the planar cross section will now become curve. That means there is a out of plane deformation happen. And if suppose the cross section will remain plane, that means this plane is extended by this amount, then all the points in this cross section move with the same value. Therefore it is independent independent of the radial coordinate. Okay, so we can see that we can say that uz is independent of radius. So also uz doesn't depend on radius. It will, obviously it will depend on z. It will depend on z. So we can say that we can conclude that ur is a function of both. That means r and z, and uz is only a function of z. Okay, so this is the final conclusion for this question. The next part of the question is obtain the strain matrix and the stress matrix for the above problem. So the strain tensor is given by, in cylindrical coordinate system, the component of a strain tensor is given by del ur over del r, half of del ur over del theta plus del u theta over del r minus u theta upon r, half of del ur over del z plus del uz over del r. This the second term is 1 by r del u theta upon del theta plus ur upon r. This one is 1 by 2 del u theta upon del z plus 1 by r del u z upon del theta, and this component will del u z upon del z, and this is a symmetric tensor, so therefore the I'm not writing this component, because obviously if you know the other components you can similarly take the symmetric one. So yeah, let's move on to the question. We have to find the stress matrix, strain and stress matrix for this problem. So del u r upon del r, so this term will remain exist because ur is a function of r. Del u r upon del theta, no, r is not a function of theta, it will cancel out. Del u theta upon del r is also cancel out because u theta is 0. U theta is also 0, so this will also cancel out. U theta is 0, so this will cancel out. ur upon r, this will remain. Ur upon del z, ur is a function of z, yes, so this term will also remain. Uz upon ur, this will cancel out. Uz u theta, this will 0. Uz upon u theta, this will also 0. So the final term that will remain in the expression of strain matrix is given by del ur upon del r 0, half of del ur upon del z 0, ur r upon r del u z upon del z, and this will become 0, 1 by 2 del u r upon del z 0. So this is the final strain matrix for this problem. Now we have to find the strain matrix. So we are using the stress strain relation in cylindrical coordinate system. So let's do this. So for isotropic material, we have sigma ij equal to lambda times trace of epsilon into delta ij plus 2 mu epsilon ij. And if we see the component wise, so sigma r is given by lambda times del u r over del r plus ur upon r plus del u z over del z plus 2 mu del u r over del r. Similarly, we can write sigma r, sigma theta theta. Sigma theta theta is given by lambda times del u r upon del r plus ur upon r plus del u z upon del z plus 2 mu ur upon r. So above, in the starting of this lecture, I have shown you the stress strain relation, so you can see here. So this is the strain displacement relation, strain stress relationship. Now I am writing here the stress strain relation. So we are not writing those expression, those term which is 0 already. So here you can see some of the terms are 0, so we are not writing that in the stress strain relationship. The next one is sigma zz, which is lambda times del u r over del r plus ur upon r plus del u z over del z plus 2 mu del u z over del z. Tau r theta is 2 times g epsilon gamma theta, which is also 0. Then tau rz is 2g epsilon rz g del u r upon del z. Yes, it's given. And tau theta z is also 0. So this is the strain and the stress matrix for the given problem. So this is the second part of the question. The third part is so that theta component of a stress equilibrium equation is already satisfied. So you can see from here that there is no stress component along theta direction, that is tau r theta is 0, tau theta z is 0, and if you see the expression for the stress equilibrium equation in theta direction, you can see from here. Yeah, so I'm just copying this relation. Yeah. So if you see the relation of stress equilibrium equation in theta direction, so there is no body force, therefore it is zero. There is no acceleration, so it is zero. Tau r theta is zero. Tau theta z is also zero. 6 tau theta r is also zero, and the remaining term is left, that is sigma theta theta upon del theta, and this is also del sigma theta theta upon del theta, and sigma theta theta is, if you see the expression of ur and uz, sigma theta theta is basically function of ur and uz, which is again ur is a function of z and r, and uz is a function of r. So it is independent of theta, so this is also 0. So yes, the third part of the question is stress equilibrium equation is automatically satisfied in theta direction. Stress equilibrium equation is automatically satisfied in theta direction. The fourth part, which is the last part of this question, is what boundary condition will be used in order to solve the above deformation problem. So basically it is glued and fixed by two rigid plate. So we have prescribed here the boundary condition. So we have prescribed 4 boundary condition along the 4 edges, because it is glued at both the ends by a rigid plate. So boundary condition along the 4 edges of RZ plane are at Z equal to L by 2, UR at R comma Z equal to L by 2, which is 0. So R at Z equal to L by 2 at any radius, displacement along radial direction is 0, because you see here that x is equal to L by 2, it is fixed by a rigid plate, it is glued by a rigid plate, so there is no radial movement. The next boundary condition is uz at any r at Z equal to L by 2 is prescribed displacement, which is delta. So because it is it can move, because it is fixed only in the radial direction, it can move along the Z direction. Okay, so therefore we can say that if we prescribe any displacement along this coordinate, along this ends, on the two ends, then we can say that at any prescribed displacement will add on one boundary condition for this problem, that is the displacement along Z direction. The third boundary condition is at Z equal to minus L by 2. So similar boundary condition will be there also, at, that is UR at R at Z equal to minus L by 2 is 0, and UZ at R at Z equal to minus L by 2 is prescribed displacement, which is delta. And there is one more boundary condition which is at R equal to 0, that is at radius equal to 0. So at radius equal to 0 there is no displacement anyhow. So UR at radius equal to 0 at any Z is 0, and due to there is no displacement in this direction, so sigma RR, that is a radial stress, because it is bounded, so we can say radial stress at R equal to 0 at any Z is also because you can see that due to radial displacement, due to zero radial displacement at zero radius, when radius equal to 0 at any particular z, there is no radial displacement. So there is some restraint which oppose the deformation happen at this point. So due to these restraint, we can say that there is some radial stress which will acting on that point. Okay, so we can say that sigma rr is present at r equal to 0 at any z. So it is bounded. Next, at outer surface, that is at r equal to r. When we say at r equal to r, that means at outer surface. So outer surface is actually the traction free. There is no traction, there is no stress, there is no external force, there is no external boundary force is acting on the surface part. So this is basically traction free boundary condition. Okay, so these are the boundary condition which will be applied to solve this deformation problem. So this is all about question number 4. Yeah, now let's move to the next problem, that is problem number 5. So the question is, the deformation of a body is such that it follows the following displacement field. It follows the following displacement field. And the field is given as radial displacement in terms of radius 0.05 r square plus 0.2 theta. Similarly, u theta is given as 0.4 times theta, and uz is given as 0.02 z plus 0.03 z square r. So the first question is, find circumferential strain. The second part of the question is, so there is only a single question, that is find circumferential strain for this problem. And the second part of this question is the longitudinal strain find the longitudinal strain. So we have two questions for this problem. The first question is to find the circumferential, and the second question is to find the longitudinal strain. Okay, so circumferential strain is nothing but epsilon theta theta, which is given by 1 by r del u theta upon del theta plus ur. And what is u theta? 1 by r 0.4 theta, which is 0.4, and ur is 0.05 r square plus 0.2 theta. So this is the value of epsilon theta theta, that is circumferential strain. Next we have to find is longitudinal strain, that is epsilon rr. Epsilon r is del u r over del r. So we have to find the longitudinal strain, right? So Yeah, longitudinal strain. So I have written the formula here. Del u r over del r. So del u r over del r is 0.05, or we say 0. If we differentiate of u r with respect to r, we will get 0.1 r. Okay, so this is the value of longitudinal, or we say radial strain. So this is a question. Now the next question is problem number 6. So this is a actually multiple choice question. So we have two statements for this question. Statement 1. The partial derivative of ER with respect to theta is E theta. And the second statement is the partial derivative of E theta with respect to theta is ER. So we have four options, and we have to say which of the following option is correct. Which of the following option is correct? The first option is both the statements are correct. Both the statements are correct. Both the statements are correct. Second option is statement 1 is true, but 2 is false. And the third option is statement 2 is true, but 1 is false. And the last option is none of these. None of above. So the question is the partial derivative of ER with respect to theta is E theta. And the partial derivative of E theta with respect to E theta is ER. So we know that del E theta upon del theta is minus ER, and del ER upon del theta is E theta. So this is the correct expression. And now move on to the question. The first statement says the partial derivative of ER with respect to theta is E theta. ER with respect to theta is E theta. Yes, statement 1 is true. And the second statement is the partial derivative of E theta with respect to theta is ER. Del E theta upon del theta is minus of ER, not ER. The partial derivative of E theta with respect to theta is minus of ER. So statement 2 is false. Statement 1 is true and statement 2 is false. So the correct option is option number B. Now the next question, that is problem number 7, is also again a multiple choice question. Problem 7. A cylindrical body undergoes following displacement. Okay, that is UR equal to 0.01 r minus 0.03, U theta equal to 0.03 theta minus 0.01 r, and UZ equal to 0. So the value of epsilon theta theta will be, so we have a question here, epsilon theta theta value 0.03, the second option is 0.02 r, the third option is minus 0.01, the fourth option is 0. So the epsilon theta theta is given by 1 by r del u theta upon del theta plus ur. 1 by r, what is del u theta upon del theta? That is 0.03. And what is ur? Ur is minus 0.01 r, 0.01 r minus minus 0.03. Okay, del u theta upon del theta plus ur minus point. So del u theta upon del theta is 0.03 theta and del u theta upon del theta. So 0.03 and this will become 0 and 0.01, and what is ur? 0.01 r minus 0.03. Okay, so del u theta upon del theta is only 0.03, so this will cancel out, and 1 by r to r cancel out. The correct option is option C, 0.01. Okay, now this is the last question, problem number 8. Physical meaning of gamma r theta denotes. The first option is change in angle between two line elements. Change in angle between two line elements directed along ER and E theta direction. Directed along ER and E theta direction. The second option is change in angle between two perpendicular line elements directed along ER and E theta direction. ER and E theta direction. The third option is change in length between line element. Change in length between line elements directed along ER and E theta direction. Directed along ER and E theta direction. The fourth option is none of these. So coming to the question, physical meaning of gamma r theta. So here it is asking about the physical meaning of gamma r theta. So the first option is change in angle between two line elements directed along ER and E theta direction. So is gamma r theta define this one? That means the change in angle between two line elements, whether it is perpendicular, whether it is parallel line elements, whether it is making an angle, making an any angle between these two line elements. So is the definition for the gamma r theta? No, this is not the definition. Actually, the definition comes from the change in angle between two perpendicular line elements, not any line elements. The line element must be perpendicular to each other, and which is directed along the two line elements is directed along ER and E theta direction. And if there is something change in angle between them, then we say there is some gamma r theta. That means there is some shear strain developed. Unless we can't say anything, because if you are taking two line elements which are inclined at some angle initially, then we can't say the definition of shear strain from these two line elements. Shear strain always define the change in angle between two perpendicular line elements along ER and E theta direction. So the correct option according to this is option number B. The fourth option is change in length between line elements. No, this is not the correct option. This is obviously incorrect. The first option is incorrect because it is mentioned that the two line elements can be anything. It is perpendicular, it is parallel, it may make some angle. So that's why the first option is incorrect. So don't be confused. This type of tricky question will always ask in the exams. So yeah. So this is the question. This is the last question for today's session. So I have solved almost around 8 questions today, and all of these questions are a very good question. I hope you understand this question, and if you have any further doubt regarding this question or any concept in the lecture which I discussed earlier, you can please reach out to me through my YouTube channel. You can write in the comment box also, and you can also ask in the next meeting, which is scheduled every Friday. The next meeting will be happen in the next coming Friday. Okay, so stay tuned, and thanks for joining today's session. So you can leave the meeting now. So thanks for joining today. Bye.